Okay, hello everybody. So what I'm going to do today is I'm going to give a quick overview of each of the slides that we have gone through so far. And by each week I will go through them. So we're going to start with the very introduction, and I will go through all four. Hopefully I will keep each of these under about an hour. And keep in mind that this first week, this was a two-part week that was all one set of slides. So I will go through the slides and one by one. Okay. All right. So to begin, we need to talk about what chemistry is. This is pretty. We've covered this quite a bit already, but it's a chemistry in specific is a study of the composition, properties, and interactions of matter. So really, it's just how matter is going to be perceived and quantified, counted, and manipulated. And so, what's important to know about this is that when we were first looking for, when humans were first looking for the secrets to matter that we had around us, that these were called alchemists, and alchemists were trying to take metals like probably lead or things like that and turn them into gold. That was the idea from the beginning, which didn't turn out to be possible, but a lot of chemistry was observed by doing this. And so if you look around you, chemistry is absolutely everywhere. It is in everything from food digestion. Your body is basically one big bag of chemistry. And there are constantly chemical reactions that are happening within that bag. And so we will discuss some of these things throughout. I don't have a huge background on chemistry that has to do with your body, but I will fill in where I can when we're talking about that. But there's also plenty of other things, so everything from textures, dyes, plastics. These all have to do with chemistry too. Literally everything in the universe is chemistry. And so first we're going to talk about the concepts that are going to drive chemistry and what is important. So observation and experimentation, these are the two key components of being a chemist. You want to observe things and then test based on what have observed. This will help you come up with a hypothesis or test that hypothesis in order to be able to further understand your surroundings, further understand everything that goes into what you have observed. Then sometimes those things can become laws of science, and sometimes they can be applied to theories. Laws are going to be the completely testable experimental observations, and then theories are going to be proven versions of these laws. These are applications of the laws for different aspects. And so if we look at the scientific the method, it's going to start with observation and curiosity. We can use this to form our hypothesis. That is going to be something that is tested, and then we will do the actual test to form the hypothesis. If this is incorrect, so we test our hypothesis. If that's incorrect, we form a different hypothesis. But if it is correct, then we can contribute to a body of knowledge, such as a publication, a book, something like that. But if it is further tested, then we must go back to the drawing board. And if you are able to test and you get things that are constant along many different applications, then that can eventually become a law of a natural law, and it could also become a hypothesis. These are pretty much very similar. One gets in a textbook, the other one doesn't. That's really it. This one would get in a textbook. Whereas the hypothesis becoming a theory doesn't necessarily get into a textbook. That would be more just in publications. We will define a substance. So a substance is something that can't be broken down into different kinds of matter. So you can't break sodium chloride down without without chemically changing it. Sodium chloride, you cannot just punch it in order to break it into sodium and chlorine. You have to do chemistry to it in order to change it. An element it's a substance that can't be decomposed into simpler substances by a chemical reaction. So that means that even if you have taken a substance and broken it down chemically into sodium and chlorine, you cannot break that down further. Those are going to be your elements. The elements cannot be broken down further without doing nuclear chemistry, which we have touched on a little bit in this, but we will talk about it a little bit later. A molecule is going to be something that is at least two atoms of one or more elements. And so we have a molecule is going to be something that we'll get into the types of bonds and stuff, but there's a specific type of bonding that occurs in molecules that does not occur in just compounds. And so you can have a molecule of N2, for example, or you could have a molecule of CO2, and you can see that CO2 is down here. This is considered a compound because the different elements are different, but a molecule, but you cannot consider N2 to be a compound because the atoms are the same in this. However, there are more than one atom, so we can call it a molecule. Compounds must have two or more different elements. Molecules can have one element or more. So a molecule is a type of compound in that. And so let's go into the different types of definitions that we can talk about. So something that is something that is classified as matter must occupy space and must have mass. So this is specific. When I was grading your first quizzes, a lot of people did not get this correct because they said that it just has to take up space. However, the mass component, or they said that it just has to have mass. Both of these have to be true. If it has mass, then it also takes up space. There is nothing that has one or the other. Even the tiniest subatomic particles, such as the Higgs boson, which is the defining factor of mass, it's a type of matter, and so it must take up space as well. Electrons, for example, they are not elements, but they still take up space and they have mass, and so they are considered matter. Ideas are something that we would not consider matter because they do not have space or mass. So anything physical is going to take up both space and mass. And of course, you guys are familiar with the different states of matter. You have a solid, a liquid, and a gas. Solids are rigid and they have a definite shape. Liquids flow and have the shape of the container that they are in. And a gas is going to take up both the shape and volume of its container. It's not going to be constrained by gravity as much as these other ones. And so when we're talking about the phases of matter, this is what they look like. We have a solid, a liquid, and gas. Solids being rigid and small, liquids taking up the shape of the container, but not the entire volume, and the gas doing both of those things. And so this is where you would see the video of plasma jumping between two halves of a grape. A plasma is a different type of matter than what we've discussed on the previous slide, but basically it is just a type of matter that is consisting of charged particles. And so you should have a better understanding of what charged particles are now that you know about what a charge is. But I will get to those slides when I get to them. Okay. And so the other thing is that no elements on the periodic table are going to naturally occur as a plasma. Okay. And so we have our periodic table here, and as you can see, no elements are plasmas. We have solids in black, liquids in blue, and gases in red, and we don't have any of these that are a plasma. We have an unknown category, and that's because not enough of these elements have been made to define whether they exist at room temperature as a solid, liquid, or gas. But for the most part, solids, liquids, and gases. There are also only two elements on the periodic table that exist as a liquid at room temperature. There's mercury right here and bromine right here. So that's just something to keep in mind for later. Physical and chemical properties of matter can be either extensive or intensive. So extensive properties are going to depend on the amount of the matter present. That is going to be their mass, their volume, and their heat. And for quiz 1, I noticed that a lot of people said that it was the amount of mass of the matter that's present, and so that's not exactly true. The amount of mass is not directly, it is an extensive property, but it does not define extensive properties. If you answer this, I gave you the point, but it is the amount of matter that is going to determine the amount of mass, volume, and heat. An intensive property does not depend on the amount of matter present. So that's going to be something that is inherent to that species that we're looking at. And keep in mind that heat and temperature are different. And we haven't gotten into that yet, so I'll skip over it for now, but they are indeed different. And so one of the laws that has been tested and and tried and true is that there is a law of definite proportions. So pure compound, regardless of its source, always contains constant proportions of the elements by mass. So that means is that if you have a gram of sodium chloride, you are always going to have this much sodium and this much chlorine. If you have 2 grams, you will have twice this much and twice this much, but it's always going to be the same ratio. And so when we're continuing, the law of conservation of mass is a very popular one. I believe there's even an anime that uses the law of conservation of mass in it. But really, this is the crux of it. You cannot destroy or create matter. It is existing, and it cannot be changed in a way that is going to be destroying it. So it will not delete out of existence, and you cannot just add matter out of nothing. There must be a total conservation of mass. So, like it says here, if you burn a piece of paper, it does not remove it from reality, it just converts it into a different thing. So for an example of physical properties, let's talk about bismuth, my favorite element. Bismuth, that's number 83. I'll put it right there. The physical properties of bismuth we can describe here. And so bismuth is it will not change in order to physically define bismuth, we cannot change its chemical composition. So bismuth, when you crystallize it in certain conditions, will make this stair-step formation, and that is one of the physical traits of bismuth. But we just jumping ahead here, we can also talk about the chemical traits of bismuth, and that comes when we're looking at the color here. So the color is actually bismuth oxide, Bi2O3, right there. Bi2O3, and when that comes onto the surface of bismuth, depending on how thick that layer of Bi2O3 is, you get these different colors of bismuth. And so so that's why that would be a chemical characteristic, a chemical property, because bismuth, when it interacts with oxygen, will change in order to have these colors. So physical property is the stair-step formation. A chemical property is going to be the color change. When we're talking about physical changes of matter, one of the easiest ones to talk about is the difference between melting, freezing, and boiling and sublimation. And so if I put an M, an F, a B, an S, and a C, then we can talk about how this changes. So melting, from going from a solid to a liquid, that would be an M. Freezing is the opposite of that. That's an F. Boiling is going to be when you take a liquid and turn it into a gas, so that would be a B. Sublimation is when you take a solid and turn it into a gas, and so that would be an S. And we can also talk about sublimation in the opposite direction here. Condensation, like the water you get on the outside of a can of Coca-Cola, this is going to be your condensation when you take a gas and turn it into a liquid. So sublimation is the only one that has a definition for going both directions. There's a technical name for something going from a gas to a solid, but I can't remember it right now, so it's not super important. Okay, so for chemical properties of matter, this is how well how well or how poorly a chemical can react with another chemical or itself in order to become a different chemical or other things. So this is a reaction that oscillates between becoming this white substance, some kind of precipitate, and this brown substance, some kind of solution. And so it can cycle through those things, and that is one of the chemical properties of this chemical. You can also talk about how easy it is to react with oxygen and heat to consider it to be flammable, how toxic it is for your body, etc. These are all going to be things, its potential for chemical reactivity. And so we can see that in many different types of reactions, such as combustion reactions. This would be considered a chemical change. So a chemical change is when you take a chemical and you convert it into something else. So it is no longer the same chemical that you started with. For example, we have cellulose, which is a lot like sugar. It's going to be C6H12O6. When you react that with O2, then you get CO2 plus H2O, our classic combustion reaction, which we've talked about before. This is the reaction that you would see with a chemical change of carbon-based carbohydrates and all that. And so this is a practice problem. I'm going to skip ahead through these, but if you'd like, you can pause here and you can test yourself again. Okay, and so these are the answers that we've gone over. Boiling water is physical because it is just a change in the state of matter. Anything that's a change in the state of matter is going to be a physical change. Anything that is a change in the chemical composition of something is going to be a chemical change. And so if you'd like, go ahead and look deeper into these and you will see how these different things work. So when we classify matter, specifically mixtures, we can talk about how they are homogeneous, meaning all the same, consisting of all the same things, or heterogeneous, consisting of different things. And so when we're talking about liquids or solutions specifically, not liquids, because as we've defined, liquids are pure, solutions are going to be mixtures of things. Oil and vinegar is going to be considered a heterogeneous mixture because you have these bubbles here. Heterogeneous means it has a different phase, so you have oil pockets and you have aqueous pockets. Whereas for a homogeneous mixture like in Gatorade, you have a solution. Usually with solutions, you can see right through them. They are translucent. This is not always the case, but especially if you have something very, very dark or absorbs light very well, like as you can see right here, this part of the solution, even though it is a solution, is so dark that you are not able to see through it. It is still a solution because all of the components inside of it are evenly distributed throughout the mixture. When we're talking about chemical purity, we're talking about things that are free from impurities, free from contamination. And so the examples that I've given here are this tungsten cube, which is very, very close to being 100% pure. The reason that it is not is because just like bismuth's color on the outside, you would have a very thin layer of tungsten oxide, so that'd be WO2 on the outside. And so for the most part, this is a very pure substance. It's really, really difficult to get something 100% pure. I've never been able to do it, and that's because atoms are very small. It's really difficult. There's really no way to even test for a single atom in a mixture. So it's highly likely that you are not going to get something 100% pure, but we try to strive for as high a purity as we possibly can. And so the other example of impurities are when you melt some kind of cube of metal or something like that, then you may see the impurities rise to the top of your melted metal, and those are all of the impurities. They're no longer part of the metal, and so they rise to the top because they are less dense. Okay. So let's continue. We'll talk about physical measurements, and this is where we get into the metric system. So just a quick recap. The metric system is a base 10 system, which means that everything occurs in increments of 10. You have 10 millimeters in a centimeter, 100 centimeters in a meter, et cetera, et cetera. It makes it very much easier to measure things than, for example, the imperial measurement system, which is the one that we use in the United States, where there are many different bases that are used. So, for example, there's 5,280 feet in a mile, there's 12 inches in a foot, and we also use fractions to describe smaller units rather than just tenths. So 1/16 is one of the fractions used in an inch. 1/32 for something half the size of a 16th. It can get very confusing, so we use the metric system because that is, in my opinion, just a better system. And I will skip by this for now, but if you'd like, you can pause here and you can take a look at all of the different base units that are used in the metric system. And so let's start with the first unit. The first unit that we will cover is going to be length. So the standard unit of the metric system is the meter, which is originally intended to be 1/10,000,000th of the distance of the North Pole to the equator, which means that there are about 10 million meters between the equator and the North Pole, but it's actually now defined as the distance that light travels in a vacuum in that much of a second. So this is calculated by using the speed of light, which is going to be 299,792,458 meters in 1 second. So a fraction of this is going to be 1 meter in a second. So it's about 3 inches longer than a yard, and we've explored meters quite a bit in this class, so I'm going to move on. For mass, the SI unit of mass is the kilogram, and that's because most of the things that we're measuring that use the metric system are measured in kilograms because they're a lot larger than atoms. So the items are, for example, you could measure yourself in kilograms. Some kind of car or something could be measured in kilograms. These are the things that we interact with daily. For the most part, we're going to be using grams, though, which are 1/1000th of a kilogram. So you can see down here, 1 kilogram is equal to 1,000 grams. And if you were to convert it to pounds, that would be about 2.2 pounds. For volume, we can derive the units of this is considered to be a derived unit. And so the reason that it is a derived unit is because when you take let's say that we are measuring a square has 2 dimensions, and we can say that goes in the x and the y. So we have a y up here and an x down here. So those are the 2 dimensions that you would measure something for a square, but for a cube, which is going to have 3 dimensions, we need to have another one. So area is measured by x times y in order to get area. But for volume, you also have z. So x times y times z is going to be what you are going to use for volume. And so it is a derived unit because it is something that you have to multiply by another unit in order to get the correct answer. And so if we were to step down from area, we could talk just about one dimension, not pi. If we wanted to step down from area, we could talk about just length. So length times width times height. So 3 different distances are used to measure volume, but length would just be x, for example. I'll put an x here, and then I'll draw the line that could be consisting of one-dimensional units. So length, when you multiply length by another length, you get area. When you multiply area by another length, you get volume. And so we use cubic meters for large things, but again, we're talking about chemistry, so we're going to be using much smaller things, and specifically, we're going to be using cubic centimeters. And so it's important to remember here that 1 cubic centimeter is equal to 1 milliliter. 1 cubic centimeter is equal to 1 milliliter. Okay, and so this is just reiterating this, so I'm going to move on. For time, we're going to use the exact same thing. There's no SI unit for time that isn't different than the imperial units. That's seconds, minutes, hours. Those are all the same. Density is another derived unit in which you were to take the mass of something and divide it by the volume, and we measure that in grams per cubic centimeter for dense items such as solids and liquids, and for very non-dense items we use grams per liter because they take up a lot more space. The standard unit is kilograms per meter cubed, but we don't really use kilograms per meter cubed. We use the ones that are mentioned down there below. Temperature. Now, when we talk about temperature in chemistry, we are pretty much going to use Kelvin all the time. That is going to be our standard unit. So it is the Kelvin. You don't use the degree symbol for that. You just use the word Kelvin. So you'd say room temperature is 219.15 Kelvin. And you can also use Celsius commonly, but Kelvin is going to be more accurate. And this is because at 0 degrees Kelvin, Kelvin is the temperature of the universe. So at 0 degrees Kelvin, then we know that everything has stopped. There is nothing moving around. And so water freezes at 0 degrees Kelvin. Water freezes at 273.15 degrees Kelvin, which is 0 degrees Celsius, but at 0 degrees Kelvin, everything freezes. So you cannot have a negative value for Kelvin, and so I'll write that. No negative Kelvin. So keep this in mind. There are no negative Kelvins ever. No negative Kelvins. The magnitude is the same, though. So 1 Kelvin is equal to 1 single degree Celsius is equal to 1 single Kelvin. Okay. So if we want to convert from one thing to another, we would take whatever degrees we have in Celsius, and we would add the number 273.15. That's because at 0 degrees Celsius, then we would have 273.15 Kelvin. So if you want to convert to Kelvin, you just add 273.15 to whatever number you have. So, for example, if you were trying to find the boiling point of helium gas, you would add 268.19, which is the degrees Celsius, to that, to 273.15, and you end up getting 4.25 Kelvin for the boiling point of helium. Which makes sense, right? We exist higher than the boiling point of helium, and so that's why helium is a gas when we are when we observe it in real life. And if we wanted to convert between Celsius and Fahrenheit, it gets a little bit more complicated. So we have Celsius, which is equal to Fahrenheit minus 32, because this is when Celsius is 0, minus 32 degrees Fahrenheit is when you would have Celsius being equal to 0. And then for the change in the slope, we would multiply it by 5 degrees over 9 degrees in order to be able to convert one number from the other. And so if we work through this example real quick, we can start here. We have Celsius equaling degrees F minus 32 degrees. If we already have degrees F, we can plug that in right there, and that's where we get this right here. We do the math that's in the parentheses first, we get 45, and then we multiply it by 5 to get 230, which we then divide by 9 to get our answer. The F's are going to cancel out to leave just degrees Celsius, and we are left with 25 degrees. If we want to go the other way, we would have to take the equation that we had before, and with algebra, we are going to rearrange it so that we are now solving for F instead. So that is adding 32 on both sides, but that is after you multiply by 9 over 5 on both sides. So 9 over 5, you end up getting a 9 over 5, and then we'll add this, and you get 32 degrees on both sides. Then you would plug in the value that you have for Celsius, and you would be able to get 77 degrees Celsius out of doing. Oh, sorry, not 77 degrees Celsius. That should be 77 degrees Fahrenheit. Okay. And so, if you would like to give this a shot, I will I will pause here so that you can do that really briefly. And then you should be able to get one of the answers, or the answers below. This is a good way to test that you know how to do this. And feel free to go back to the previous slide so that you can see exactly how to do it. Okay. So, for uncertainty, this is what our first lab was all about. We want to measure uncertainty in a number, and we want to do this by using the 3 different parts of a number. So, the 3 different parts of a number in chemistry are going to be the size of the magnitude of the measurement. This is going to be represented by a number. Let's say that we have 9.0 degrees Celsius, so the plus or minus 0.01 uncertainty. So the size of the magnitude of the number is going to be 9.0, and I'll make it blue so we can see. The number will be 9.0. The standard comparison of the measurement is going to be the unit, and so I will underline that in yellow. It's kind of hard to see, but degrees Celsius will be the unit. And then the uncertainty is saying, well, our information is limited by the amount of, or by the precision of the equipment that we have. So the uncertainty represented by 0 plus or minus, that means you're either going to add or subtract 1/10 of what is being measured, so that is going to be 0.01. 1/10 of what's measured is going to be 1/10 of the lowest number that could be measured. So with this scale, you have 2 significant figures. You have 0.0 and 0. You have 1 decimal point, which means that the lowest number you can measure with this is 0.1. And so 1/10 of 0.1 is going to be 1 over 10 is going to be 0.01. And so this is what your uncertainty is. So if we're talking about things that we are counting, then we are going to not consider uncertainty. So some values always have exact values. So for example, if you've counted 12 inches of something, then you have counted exactly 1 foot. If you counted 13 inches, then that is no longer 1 foot. This is always going to be true, where there are a certain number of inches in 1 foot. For example, 1 inch is exactly 2.54. These are always going to be exact numbers, and so we can consider them to have infinite significant figures, which we'll get into in a second, but we already have talked about significant figures, so I'll bring those back up. We have infinite significant figures, which means that we don't have to consider the significant figures when we're doing calculations with these. For measurements, though, there is going to be uncertainty because our piece of equipment is never going to be able to be as accurate as we would like it to be. There's always going to be practical limitations. So, like, even if you have something that's very, 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 very precise, let's say you have an atomic clock that can measure 1 times 10 to the negative 30th of 1 second. You don't know if you have 1 times 10 to the negative 30 second. You will not be able to measure the 1 times 10 to the negative 30 seconds of 1 second. It's not going to work because you don't have a piece of equipment that is precise enough to do that. It's just not possible to do. So, and that's just the way that numbers work because of the fact that you can keep going, you could keep adding. Even if you invented a piece of equipment that would have 1 to the negative 32nd accuracy of 1 second, you will never be able to do that for 1 to the negative 34th or 1 to the negative 35th. It's just going to keep going and going and going because it is just not going to be as accurate. There's just no way to get there. And so that's when we start using uncertainty measurements. And so this is an example of an uncertainty measurement that we have. We're going to we can only be accurate to 1/10 of the smallest recording that we have. So if this is milliliters, then we would record the number like this. We assume this is 21.5. We could assume that it's 21.5. We know that it's accurate. We know that it's accurate up to 20, the 20 line, and the 1 line. That's our smallest number, so 21. And then we're going to add one significant figure to this and take a guess at what it is. So it's going to be 1/10 of the smallest measurement. Our smallest measurement is to the 1 milliliter, and so we can estimate the space that comes after it. It looks like it's about halfway between 1 and 2, so I can say that it's about 21.5 because 21.5 is going to be halfway between 21 and 22. And so this is my uncertain digit. Okay, my uncertain digit is going to be 1 past what my smallest measurement can be. Okay, and so I will give you a second to give this a shot. That looks horrible. I didn't realize that. Well, whatever. So yeah, so go ahead and take a guess. The answer that I'm giving is right here, and because you are accurate to, let's see, these are centimeters, so this is a millimeter, and so we can guess. So if these are centimeters over here, this one would be a millimeter, so we can guess to 1/10 of a millimeter. So any number between 16.80 and 16.90 is accurate. And so go ahead and give it a shot, and then I will proceed. Okay, so let's talk about accuracy and precision. This was on your homework, and most of you got this exactly right. And it was also an exam, I believe. Possibly. But anyway, precision is how close your repeat measurements are. So precision would be represented as very close together. However, accuracy is going to be how close together your answers are to the actual value. If you have something that's accurate and you are able to get a very close value to the accurate value, then that is that if you are accurate, then you will be able to get a value that is close to the actual value. And so if you wanted something where some of the measurements were accurate with low precision, it might look something, oh my God, it might look something like this. Where you have a spot that would be here, but if your precision is bad, then you might have other recordings that are not on the target, but at least one of your recordings is going to be accurate. And so for significant figures, which we've talked about a little bit already, significant figures are going to be the way that we determine the accuracy. And they're important because you are only accurate to your least precise piece of equipment. So in experiment 1, we took a beaker and we were able to determine its accuracy or its precision based on the number. And so beakers are famously not precise at all. And we can see here that there are only 3 significant figures here. We have 1, 2, and 3, and these are going to be insignificant otherwise. So if you are able to make one determination past the lowest decimal place, which is the ones place, and so any recording that you made would be to the 10th place. So let's say that we had filled it right here with liquid, then that would be 200, this is going to be 250, and then this is going to be 275, and so that's 300. And so 275.1 could be a good guess, but that is as close as you can get to the actual amount of liquid that would be in this beaker. All right. And so, for example, we can count the number of significant figures in these values. So for non-zero digits, these are always significant. Non-zero digits are always significant. So if we look at this first number, the 1 is not 0, so that is going to be significant. Captive zeros, that means zeros that are between 2 non-zero digits, like here, are going to be significant. So that's why we have 3 right here, even though we only have 2 non-zero numbers. Trailing zeros are a little trickier. So trailing zeros, when they are to the right of a decimal place, are considered significant. So, for example, a trailing zero is a number that comes after a non-zero digit. Since this number is to the right of a decimal place, then this is a significant figure. When you're using scientific notation, then all of the numbers that are not included in the in the times 10 to the some number, those are all going to be significant. And so those are all significant, but then we get to the non-significant numbers, which are leading zeros. So in this same one over here, you have 2 numbers that are coming before a non-zero digit, and those are going to be leading numbers, and they are not considered significant. That's because you could put this into scientific notation, and you'd be able to get rid of those numbers. Trailing zeros when there's no decimal place, which is not shown on here, but I can give you an example. If you have 100, 1000, this is 1000. However, there's no decimal place, so this is only going to have the 1 significant number. This number, 1000, if you wanted to say that they were all significant, then you would put a decimal place after all the zeros, and so now we have, before we had 1 significant figure, now we have 4 significant figures. Okay. And I've already covered this, but we have captive zeros between two non-zero numbers here and here. So this is a captive zero, so it's significant. We have three significant figures here. The trailing zero does not have a decimal place, so that is not significant. I'm going to put an NS for non-significant. These numbers are before a non-zero digit, so they are not significant. This one is after the decimal place, so that is significant, and this one is between two non-zero numbers, and so we can say that these are significant. And so this would have four. We have the non-zero numbers, 1, 2. We have the captive number here, and we have the trailing after a decimal place, so that would be 4 sig figs. And so I've already covered this, but in some cases it's going to seem like there are certain significant figures when they're not. If there is no decimal place, then any trailing zeros are not going to be significant. So this one has 5 significant figures. You have 4 non-zero numbers and 1 captive. So it's 1, 2, 3, 4, and then 1 captive. So that is 5 sig figs. But now you have a decimal place, so that is 1, 2, 3, 4 non-zero numbers, 1 captive number, and then 1 that comes before the decimal place, but there is a decimal place, so this counts as another significant figure. And so that is going to be 6. You don't have to do this for numbers that do not end in 0. So if you have 4901, then that is going to have 4 significant figures. You have 3 non-zeros, so that's 1, 2, 3, and then a captive 0. The decimal place there does not do anything because this number is not 0. Non-zero numbers are always going to be significant, so we don't care about there being a decimal place there. So please don't put one. We have 1, 2, 3, and then the captive one, which is right there. And so this is, again, going to have 4 significant figures. Okay. So for scientific notation, this is something that I see people struggle with a lot, and so I will go into a bit more detail here. So for scientific notation, we're going to get rid of all of the different, all of the insignificant figures. And so, since there's no decimal place here, there are only 1, 2 significant figures. So, we will get rid of all of those, 2.9. And then, we will determine how many significant, or what to put this exponent as. And so if there was a decimal place here, it would go right at the end of the number, right? And so we can count how many hops we need to get to put only 1 digit to the left of the significant, or 1 digit to the left of the number that we're trying to get to, and the rest can be considered part of the digits that are going to add up to go right there. And so we have 1, 2, 3, 4, 5, 6, 7, 8. Ooh, my mistake. That should be an 8, not an 8, not a 9. So we'll hop once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8. Oh my gosh. Okay, I take that back. That is supposed to be a 9. So 9. 2 times 9, 10 to the 9th. And so yes, that was my mistake. That was improper counting. But basically, you want 1 digit to the left of the decimal place, and then all of your remaining significant figures are going to go to the right of that decimal place. And then what you're going to do is you're going to add a multiplier so that if you were to do this math, 2.9 times 10 to the 9th, you would get back this number right there. And same thing at the bottom right here, you have 6626 with 34 zeros in front of it, and so that is how we would get that number. I'm not going to do all that. And so take a minute and just soak this in, and we will continue. So significant figures are going to be those that are included in scientific notation. If you do not have many significant figures, then you are going to have only a few significant figures in your calculation. And so this will be on the quiz, converting numbers from scientific notation to, the exam, converting scientific notation back and forth. You only want one digit to the left of your decimal point. Only one digit. Any of the other digits is going to go to the right of the decimal point. And those are going to be the significant digits only. And remember that when you have this multiplier times 10 to the y, whatever the number is, you do not include those in your count for the significant figures. So we only have one significant figure here, even though there are technically three digits, right? You have 1, a 0, and a 0. And I'd also like to remind everybody about exponent rules, just very quickly. So any number, if you were to, actually, what I'll do is this, just as a quick diversion. Oh, not that. Not that either. Let's go and just go back and make a new one. Go away. So if you have 10 to the 1, any number, you could have 8 or 9 to the 1. You could have 100 to the 1. Any number to the first power is going to be that number, whatever that number is. So that's going to just be 10. There you go. That's it. 9 to the 1 is going to be 9. 100 to the 1 is going to be 100. Any number to the 0 power is going to be 1. So if you have 1,000,000, 000 to the first power, to the 0 power, that is going to be 1. It's equal to 1. Doesn't matter how big that number is. All right? And another thing that you can remember for exponents is that if you have two exponents, let's say 10 to the 9th, and you multiply it by 10 to the 8th, as long as these values, as long as the numbers that are being taken to the exponent are the same, you can just add the two exponents together. So 9 plus 8 is 17, so we would say 10 to the 17th. You cannot do that for something like 9 to the 9th times 8 to the 8th. That would not work. This is not going to work to, you're not going to get a number that is going to be the same. It has to be 10 to, or it has to be the same base value that is raised to an exponent. And the same thing works for division. If you have 10 to the 20th divided by 10 to the 10th, you're going to take those exponents and you're going to subtract. So that's going to be 20 minus 10. That'll give you 10. So your value is going to be 10 to the 10th. Okay, that was just a quick intermission real quick, but let's get back to where we were. So I'm going to move on from this, but let's keep in mind that you need to know whether or your exponent is going to be positive or negative. And so these are the rules that we would do to do this. I apologize for getting that wrong before, but if we were to imagine there is a decimal place right there, all we need to do is count the number of times it needs to hop over to get the number that we are desiring in order to find out what that decimal place is. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And so we would put a 9 up here, and that would be the number that we use. The way that I'm used to doing it is you're going to pick the number that you know is going to be in front, and then any of the digits up to the decimal point are going to be added together. It's the exact same thing, it's just a different way to look at it. We know that this number, these numbers are all going to come together Well, the number of digits is going to come together, and that's the number that you're going to put right there. So that's going to be 9 digits, and so that is going to be 2.9 times 10 to the ninth. Either way you do it is fine. When you move the decimal point, when we're talking about the moving of the decimal point problem, when you move the decimal point to the left, that is going to give you a positive exponent. Moving the decimal point to the left gives you a positive exponent. So you can probably guess that if you move the decimal place to the right, you'll get a negative exponent. And so for smaller numbers, you can do the exact same thing. Just count the number of hops it takes. So we have 1, 2, 3, 4, 5, 6, 7 hops. And so it's moving to the right, and so we have a negative exponent. You can also count the number of zeros. For numbers that are smaller than 1, as long as there is a single 0 out in front, then you know that you can include that in your count. But there are 1, 2, 3, 4, 5, 6, 7 zeros in front of the number that you'll be putting in the front of your scientific notation. And so 7 zeros gives you a negative 7 value right there. And so when you're doing this, just be sure of what you are looking at. So 10 to the negative 7th is going to divide your number by quite a bit, right? You're going to have a much smaller number than you would otherwise. It's also like saying 4.056 divided by 10 to the 7th. These are equivalent statements. You're going to get the exact same number out if you were to do this math or if you were to do the hopping thing. And so just keep in mind the sign of your exponent that can trip you up later on. Okay, so this is the difficult part when it comes to significant figures, is going to be your multiplication, division, addition, and subtraction. And so multiplication and division have different rules than addition and subtraction, all right? So addition and subtraction are going to have one set of rules, which we'll get into, and multiplication and division are going to have another one. When you multiply or divide, you're going to pick the number that has the fewest number of decimal places, and that's what you're going to use to calculate the sig figs at the end of your calculation. When you add or subtract, you're not looking for the fewest number of digits, you're looking for the fewest decimal places, not the fewest number of digits, okay? So, when we're talking about rounding, if you end a number in 0, 1, 2, 3, or 4, that number gets rounded, the next number gets rounded down to 0. And so, if we were to, I'll give you an example for each of these. 0.070, if we're going to round this down, this is our final digit, and so we're just rounding this down to this number. 2.11, this is our final digit, so we will go with 2.10. And just for significant figure's sake, we'll put a decimal point there to show that we have a number that ends in 0, even though all of the numbers are to the left of the decimal place, and we have the same number of sig figs. For 5.12, this is our final number. We have 5.10. 31.63, this is our final number, so we have 31.60. For 1.4, we have 1.0. So it gets rounded down to 0. The numbers that are higher than 4, all the way up to 9, you're going to round up. So for 0.079, that's 0.080. For 218, that is 220. For 5.17, we have 5.20, 31.66, 31.70. So you're just going to round up to the next unit of 10. So for 1.5 times 10 to the 3, I'll put a 10 to the 3 here. 1.5 times 10 to the 3, that's going to be 2.0 times 10 to the 3. And so sometimes it can have a chain effect. So if we are going to say 1.09995, we round up 5, that's going to round up this, right? to 10. So that would be 1.0999 and then 10, right? But that's going to, a 10 rounds up the next number. So that is going to continue and continue until you get to this number right here. So you're going to end up with 1.1000, however many it is. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so that would be your chain effect going on. Sometimes that does happen, so just be aware of it. Okay, when you multiply two numbers, you don't want to trim the sig figs until the end. This is true of any kind of calculation. Do not trim your significant figures until the very end, no matter what it is. If you have mixed calculations, we will also wait until the very end to trim those significant figures. So we have this number times this number. It's going to give us this number. Now, our fewest number of significant figures is going to be 1.02. And so when we are trimming for that, we are going to trim to have only 3 significant figures. And so this is the number that we get out of it. So we could keep it here by placing a decimal point at the... Nope, we could not do that. If we place a decimal point at the end, then how many significant figures does it have? Well, we have 1, 2, 3, and 4, right? Because that 0 is now going to count as a significant figure. So that has the incorrect significant figures. So what we need to do is we need to convert this to scientific notation. When we convert it to scientific notation, then we can get rid of that unused number, and we are left with this, 2.40. There we go. Okay. For division, it's the exact same thing. We want to divide one number by another. And if you are going to, sometimes you will need to have a value that is going to be the incorrect value that you want. And so if you're not finished with your calculations, let's say that this number is going to go into something else, then you want to trim your significant figures by the by a one more digit than the largest number. So let's say that we weren't done with this calculation, which we will be very quickly, but let's say that we weren't done, we're going to do something else with this number. Let's say we have to multiply it or something. Then we would count the number of significant figures we have, 1, 2, 3, 4, and we're going to end up with a number that's going to have 6 significant figures, but you need at least one more number than the largest number. And then when we're finally ready to do our calculations, we'll do the exact same thing, and we're going to trim and get rid of this. Let's go ahead and just let this wash over you for now. Don't think about it too much. We'll come back to that in a bit. Okay, all right, I'm going to continue. For addition and subtraction, these are a little bit different. So what you want to do for these is you want to take the numbers and you want to line them up and then find the lowest number of decimal places and draw a line that goes right by the lowest number of decimal places. Anything to the right of this line is not a significant figure, and so we don't care about it anymore. Once you add these together, though, then you will have trimmed correctly your final answer, and that will be your significant figures. Okay? All right. I'll give you a second to do this, and I don't have the answers on hand, and I've got a lot to do today, so go ahead and give this a shot. I will tell you the number of significant figures that you need from these, though. Okay, so from this calculation, I see that this is just multiplication and division, which means that 2 significant figures is going to be our answer. For this, we will follow PEM BAS to determine what our final significant figures are going to be. And so we would do this calculation first, which means 3.38 minus 3.01, and so we will cut that off right there. We have the same number of significant figures. What are we left with? 0.27. Okay. And so this has, we have two significant figures in this. So PEMDAS, we do the parentheses first. If there's any exponents, we do that. Then we do multiplication. And so we're not done with this calculation. So 0.27 is going to be the a number that we have. But we're going to base our final, I'll write it down, final calculations are, final significant figures, final SF based on final calculation. Okay, and so since we're not done with this calculation, even though the number of significant figures is 2 here, we have a number over here that has 58.61 that has 4 significant figures. And so what I'm going to do is I'm going to add 3 significant figures to this number. Even though we just took them away, I'm going to add 3 of them because we're not done with our calculation and we want as accurate a number as possible. And so I will add this because our final calculation is going to be whatever these numbers are together multiplied by, these numbers are multiplied by each other, this number minus those numbers multiplied by each other. And so we'll end up with something with, I'll replace these with x's. So x, 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 x. We're going to have 1.48 minus x point x, 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 x. And so now we can trim. Now we can do our trimming. Now that we have given an extra few decimal places to this number here and this number here, because our final calculation is going to be where we do our sig figs. Okay? And so whatever this number is going to have only 2 decimals. Okay, and so for this number, we have 5.41, 5.41 minus 0.398. And again, this is our only calculation, so we don't care about that 8. And so our calculation here is going to have 2 decimals. Okay. All right. And so dimensional analysis. So this is what we're going to use throughout this class. This is our stoichiometry starting point. Right? So dimensional analysis, this is what we start to use this this kind of format for, where I like to make it called a train track or something, I don't know, a ladder. But basically, we're going to use conversion factors. And so we're going to use common conversions in order to convert from one thing to another. And so this is important. So if you're watching this video, this is important. Please pay attention to it so that you know exactly what will be covered on the exam, because this will absolutely be on the exam. This is the fundamentals of calculations in chemistry, so it's very important that you know this. So to use this train track method, or the ladder method, you're going to put what you need in the starting left, whatever you have in your hand, whatever you're given is going to be in the top left corner. And so this should actually be 1.0 because we are taking 1.0 inches and turning it into feet. Whatever you want to end up with, whatever the units are that you end up with, are going to go on the right-hand side. And so that's going to be where you end. You don't put anything in this corner right here. This is going to be 1. So that anything that it is divided by is just itself. So you could either put nothing or you can put the number 1. And then you're going to use conversion factors. So you're going to put whatever you're starting with here. Whatever it is that you are going to use to convert needs to go on the bottom, and we need to cancel out units. So 1 inch, gone. There are 12 inches in a foot, so the inches part is gone. And all you're left with is the top and the bottom. The only units you have left are the feet. And so you can then simplify this and say that we are going to take the top and multiply it by, multiply all the numbers that we have there together. You can imagine these vertical lines as multiplications. So 1.0 times 1, and we will divide it by the bottom multiplied together. So remember that there's just about a 1 here, or you can put nothing there. It doesn't matter, but it is technically a 1. So that's 1 times 12, and that's where we get 12 down there. And then we'll multiply it together. We get 1/12 of a foot, or 0.0833. For significant figures, since this is a multiplication, we will take the lowest number of significant figures. Remember that these have infinite significant figures. They have enough that they will always have enough so that you can trim, not based on any kind of conversion, just based on the numbers that are real, the measured numbers. And so we will account for sig figs and say that there are just 2 because there are 2 sig figs here. And there are 2 sig figs here. Okay. And so, using dimensional analysis, we can go ahead and see how much in, what is this, angstroms? That's the unit that we use to measure atoms. Or how many angstroms 1.35 fruit by the foot snacks are going to be. And I will give you a chance to do this on your own, and then we will go over it. And actually, I believe that I'm going to stop here because there's another video explaining all of how to do this, okay? And I'm going to move on to the next one. All right. Have an excellent day, and I will see you in the next video.